Welcome to the Space, Time, and Transport in Petrology and Geochemistry 1. I would like to introduce our first speaker, is Bill Carlson, and he's going to be speaking about compositional and ionic-size controls on the diffusion of divalent cations in garnet. Actually, before I do that, I want to just let the speakers know that the timer is set up so that at 12 minutes it will turn yellow, and at 14 minutes it will turn red, and 15 minutes is the end of your presentation. So, all right, well, Bill, welcome.
Well, thank you, Sarah, and thanks to all the organizers for putting together what looks to be a really good session. I'm grateful to have been invited to talk. I'll start out here at the nanoscale. The development of compositional zoning in garnet and its relaxation by diffusion means that rates of diffusion in garnet govern a whole host of important petrologic processes. And yet, we really have no theories that can adequately explain the rates that we've measured for this process. So what I hope to do this afternoon is take a few steps in a direction that might actually lead towards such a theory. In a nutshell, this is my talk. The problem is here on the left. For these divalent cations, there are inexplicable systematics in their diffusivities that we just simply haven't been able to explain. What I'm going to do is present a series of atomistic simulations that provide at least qualitative explanations for some of these things. And the basis for that is the calculation of the relative energies of various atomic configurations that are encountered during the diffusion process. I got into this because of some systematics that came out unexpectedly from my 2006 synthesis of garnet diffusion data, which now allows us to compute the diffusivity of these divalent cations at any chosen temperature, pressure, oxygen fugacity, and host garnet composition. And an example of what you see if you do that is here. These are data at 1200 degrees C, 1 bar, and a graphite oxygen buffer. On the vertical axis is the logarithm of the diffusion coefficient, natural log, and on the horizontal axis we have a measure of ionic radius. Now this quantity here, delta, on the horizontal axis is actually a misfit parameter. So delta has the value of 0 for an ion that has a radius which, when added to the radius of an oxygen ion, sums up to exactly the bond length in the particular site that that ion sits in. And so oversized ions have values that are positive and undersized ions have values that are negative. This illustrates two key violations of our existing theory. One is this very strong compositional dependence here, which should be paired, under existing theories, with an equally large variation in the activation energies. But in fact, measured activation energies for self-diffusion are very close to one another. They're all within about plus or minus 6% of their central value. Another problem is that we see in these data slower diffusion of smaller ions when those ions are undersized. And of course, existing strain theory would tell us that smaller ions should always diffuse more rapidly. Then on top of that, take note of this beautiful quadratic dependence that we see here. The model itself has nothing in it at all that depends on misfit, and so I think that this well-defined quadratic dependence can't be simply coincidence. Well, if we try to explain these ideas with elastic strain theory, we would start here. This is just a diagrammatic illustration of what would have to happen if we have diffusion by a vacancy mechanism. As an atom moves into an adjacent vacant site, it has to shoulder aside the atoms that form a barrier to its path, and that requires that work be done in order to reach that transition state. And elastic strain theory is very simple. The idea is that the motion of a larger atom requires more strain, which requires more work and results in slower diffusion for that larger atom. Well, sometimes this theory works. It's quantitative. It predicts that the logarithm of the diffusivities, when plotted against this misfit parameter, should define negatively sloping limbs on parabolas that have positive curvature. And these data from Van Orman et al. Actually fit that sort of relationship. But here are those garnet data that we saw a moment ago, plotted at exactly the same scale. And of course, the differences here are quite dramatic. Now, they're so dramatic, in fact, that some critics have claimed that this has to be just an artifact of a bogus model. And I'm confident that that's not the case, and let me take a minute to address that. These are, after all, just fits to existing data, so we shouldn't be surprised to find in the original data set examples of some of these things. Here's one example from Chakraborty and Ganguly's data that clearly shows slower diffusion for smaller atoms when they are undersized. So here we have manganese diffusing half an order of magnitude more rapidly than these smaller atoms in spessartine-almandine couples. And when I went looking in the literature, I didn't have to go too far to find examples of similar behavior. Here again, plotted at exactly the same scale. We have data for forsterite, periclase, and tephrite, the manganese olivine, that behave very similarly to what we see in garnet. So I conclude that these systematics are real, that they're shared across multiple mineral groups, and that they are really highlighting a fundamental gap in our understanding of diffusion in ionic solids in general and in minerals in particular. So I've tried to approach this using atomistic simulation. These are lattice dynamics or molecular statics calculations. The basic overview here is that we define the potentials that interact between atoms. We identify the configurations that the atoms take during diffusion. We relax those structures to minimize the lattice energy in each of those configurations, and then we compare those minimum energies to see what those energy differences are. Simulations I did use the GULP program written by Julian Gale, and I'd like to thank him for his help. We follow the protocols of Van Westerenen et al. That means the interatomic potentials are Born ionic models with integral charges, two-body Buckingham potentials, plus a three-body term for oxygen, silicon, oxygen bending. Polarizability is treated with a shell model, but only for oxygen. Lattice relaxation is explicit out to 10 angstroms and with a Mott-Littleton approximation beyond that, and all of these are in the static limit. So we have to focus on the structure of garnet. Here's a little piece of the pi rope structure. You can see tetrahedrally coordinated silicon in dark blue, octahedrally coordinated aluminum in light blue, and the atoms of primary interest are the yellow ones, which are in eightfold dodecahedral coordination. And if we focus in on those, you can see that each of those dodecahedra shares 4 of its edges with neighboring dodecahedra. So if we introduce a vacancy in the center, any one of those 4 neighbors could jump into that vacant site in diffusion. And that means that we can just single out one pair of those dodecahedra for analysis of the energetics. So I call this the diffusion group. There it is. And this group takes on a variety of configurations during the diffusion process. If the initial state is the normal lattice shown here, the first thing that we have to take into account is the energy that is needed in order to substitute a different atom of a different kind into that same site. So I'll call the difference in lattice energy between those 2 configurations the substitution energy. In order for diffusion to take place, then we have to have a vacancy over here so this atom can move into it, and that has to be paired with a cation vacancy as well. And so the difference in lattice energy between these 2 states, or these 2, I'll call the paired vacancy formation energy. And then the diffusion jump itself, if we start off in this initial state, it moves through a path sort of like the one shown here, back to its final state. Those are the same energy. This is the maximum energy along the path, and the difference between the initial state and that state is the migration energy. So these are the types of energetics that we're going to investigate. Let's start with the substitution energies. The substitution energies are plotted here on the vertical axis, and they are shown for each of the 4 divalent cations in each of the corresponding end members. And they're plotted on the horizontal axis as a function of the unit cell dimension of those end members. It's very clear here that oversized atoms increase the lattice energy. That's not unexpected, but maybe surprisingly, these undersized atoms actually reduce the lattice energy. And the reason for that has to do with the way in which the bond lengths adjust in order to accommodate these misfit ions. So plotted at the lower left are bond lengths for the relaxed configurations, and in each of these groups of 8 oxygens, 4 of them are closer in and 4 of them are further out. So these are the closer in, these are further out. And what's remarkable is that these MO2 bonds preserve near constant lengths across all of these hosts. So that means that if, for example, we have this as grossular and we substitute in a magnesium atom, these 4 nearer oxygens snuggle in around it, decreasing their bond lengths as shown here. And the same thing happens to a lesser degree for the outer atoms. So what we're doing is binding this smaller atom, this undersized atom, tightly into that site. Looking at the paired vacancy formation energies, again plotted in exactly this same fashion, this is a marked effect, and we can see that the creation of these vacancy defects is energetically greatly favored in these more expanded lattices that you see here, grossular on the right. And in addition, if we look within any one given host, you can see that the energy cost is higher when the vacancy pair is adjacent to a larger ion. And these have very important impacts on the diffusion, because we know from thermodynamics that the vacancy concentration increases exponentially as the vacancy formation energy decreases. So over here in Grossular, where we have a lower vacancy formation energy, we have a higher concentration of vacancies, which produces a larger diffusivity, and the opposite is true at the other end of the scale. And because the diffusivity is proportional to the vacancy concentration, that's why the diffusion is faster in these expanded lattices. Note also that within a given lattice, the larger ions have a higher vacancy formation energy, and that implies slower diffusion of larger ions. Well, that explains what's happening over here on the oversized half of the diagram, but it's exactly the opposite of what we see on the undersized part of the diagram. So we have to look elsewhere for that explanation. And it comes from the migration energies. When we calculate the migration energies, what we see here is that we do in fact have higher migration energies in lattices with larger ions, so that accounts for the slight positive slopes on all of those with of a given color. But in any given lattice, the migration energy is greater for the smaller ion, exactly the opposite of what elastic strain theory would predict. And that's a result of the tighter binding of those smaller ions due to the bond length changes when we do the substitutions. In passing, if we look at self-diffusion and what these migration energies are, they are actually in reasonable agreement with measured activation energies, although they're not exactly the same thing. So I'll close here by looking at what the implications of these things are for diffusion rates, each in turn. Starting with this strong compositional dependence. We observe strong compositional dependence, but with very similar activation energies. Why should that be? Well, the answer is that this vacancy pair formation requires substantially less energy in these expanded lattices. So we have the ability to diffuse much more rapidly in those lattices. And the point is that that's the key factor. That's the main thing. Most of the strain energy is introduced when those vacancy pairs are created. The additional strain required to reach the transition state is small and is, in fact, comparable for all of these compositions. So that produces these very similar activation energies. We observe slower diffusion for smaller ions when they are undersized on the left side of that diagram. Why is that? Well, the answer is that this constriction of bonds between M and O2 oxygens binds those undersized atoms more tightly within their sites. And so those migration energies therefore increase with the degree of misfit for undersized ions. So that would explain why we have this increase in diffusivity for larger ions on the undersized portion of the diagram. On the other hand, we see slower diffusion for larger ions when those ions are oversized. And the explanation for that, I think, cannot be migration energies, which was what elastic strain theory would predict. Instead, it has to be related to what we see here, that the vacancies adjacent to smaller atoms are energetically more favorable, lower down, than the vacancies adjacent to larger atoms. So once again, it's the local vacancy concentrations that impact the diffusivities. And finally, we have a systematic quadratic dependence on this misfit parameter, these beautiful curves that you see here. Why is that? I don't know. Beats me. We still lack a quantitative theory that can link all of these effects together to explain this quadratic dependence on misfit, so please stay tuned. Thank you.
Great. Well, we have a little bit of time for questions, if there are questions. John?
So there's considerable predictive power. For example, the diffusion rate of trace elements, that are plus 2. Any information about other elements besides these major 4?
John has asked if there's other information about the diffusion of other elements like trivalent trace elements in Garnet. Is that the question?
Well, specifically divalent elements. The trivalents are different.
Trivalents are different. Is there other information on divalent elements in Garnet? There must be some small amount of information out there, but I'm unaware of it. Ralph, did you have a question? Rolf has asked, why is it sometimes the case that elastic strain theory works and sometimes it doesn't? It's, for example, that in diopside we see the opposite behavior from garnet. And I can only say that it must have to do with the particular energetics associated with the relaxation of the structures around these things. Garnet's rather unusual in that it pulls 4 of those atoms in while leaving the other ones out. And I suspect that ultimately it's going to trace to something like that, but I don't have the answer now.
All right. Well, thanks so much, Bill. Great. Our next speaker is John Bowman, and he's going to be speaking to us about geometrical and geochemical properties of isotope exchange and reaction fronts in the Alta, aureole, Utah, evidence for scale-dependent heterogeneity and anisotropy in permeability of marbles. So we have this pointer. Okay. Yes, and why is it 14?
Sorry for the delay, Jeff. Okay. Yeah. Oh, and I just advanced them here, right? Yeah, great. Yeah, well, good afternoon. It's a pleasure to be here today. So I want to talk about some development at both large and small scale of heterogeneities that produce dispersion of isotopic exchange fronts. And so, and this will be in the Alta aureole. So infiltration-driven metamorphism has produced a prograde sequence in the aureole from talc, tremolite, forsterite, and periclase, first noted here by Moore and Carrick. That infiltration-driven metamorphism has also created carbon isotope depletion in the inner part of the aureole and oxygen isotope depletion further out into the aureole, and that sets up then some carbon and oxygen isotopic exchange fronts that are developed in these high delta 18 and delta C13 marbles here, and their approximate locations are shown here by these 2 bands here. Now, our previous work, we noted that the positions here of the carbon and oxygen fronts in the periclase isograd were compatible then with outward flow of fluids from the Alta stock out into the aureole. And Steve Cook did some 2-dimensional modeling of this, and the patterns here of the oxygen front and the periclase front can be duplicated with a relatively short flow time of about 5,000 years and a time-integrated fluid flux of around 3,000 meters cubed per meter squared. We haven't really talked much about the carbon front, so I thought I'd talk about that today a bit. Okay, so the next 2 slides are of plots of the delta 18 and delta C13 as a function of distance from the intrusion that define these fronts. And what you certainly notice here is yes, there's a lot of dispersion. That is, at any given distance from the intrusion, there's significant variation in delta 18 value. For any given amount of depletion, say this gray bar here, then there's a significant variation in the position of that depletion here. Okay. The red crosses here mark then 2 determinations of the center point of the exchange front here, and it's defined by the midpoint here between the delta 18 values of the marble protoliths here, which are about 26 per mil, and values of the equilibrated carbonates next to the intrusion of about 11 per mil here. The first one is, the nearer one is at 350 meters from the contact. That's a value that I get from the 1-dimensional modeling that I'll show you here in a minute. And the farther one at 410 meters is the value that Steve Cook gets for the midpoint, center point of the front, with a simultaneous solution of the periclase reaction front and the O18 depletion and the exchange front here for oxygen. Okay, and then here's the carbon plot versus distance here. And again, you can see there's significant dispersion here of the delta C13 values. Similar to what we were just looking at for oxygen. The red cross marks an estimate, my estimate for the position of the center point here at about 100 meters from the contact. And in both the last slide and in this one, the blue band here marks the position on average of the Periclase reaction front, which is about 200 meters from the intrusive contact. Okay, so on this next slide, what I've done is just taken one-dimensional models here for 5,000 years of flow at variable diffusion dispersion coefficient here. Okay, so there's three profiles shown here, and you know, we can look the value here at a diffusion dispersion coefficient of about 2 times 10 to the minus 7th meters squared per second. That seems a little steep here. Sort of misses the majority of values here in the inner forsterite zone that are somewhat depleted. Contrast the value of 2 times 10 to the minus 5th meters per second squared, sort of misses the maximum O18 depletion that extends out here, maybe out to close to 200 meters from the contact. And the value at 10 to the minus 6 here seems to be about right here for the profile here. And the key point here is that, you know, no matter which sort of value or profile you put in here, you know, all of these are really high diffusion dispersion coefficients. And what this means then is that the value of the dispersivity that one would calculate would be on the order of tens of meters and perhaps getting close to 100 meters. So it really indicates a rather heterogeneous permeability system here for the aquifer. Okay, the values, there's some variations you can play with the fluid flux here. So that's what I've done here is just, again, here's the two estimates of the positions of the center point here at 350 and 410 meters. And these are the profiles constructed at 2 times 10 to the minus 6 value for the diffusion dispersion coefficient here. And what I've done is this is to remind me, what I've done is I've sort of emphasized that the solid symbols here, which are in close to the intrusion here, are the Periclase bearing samples within the nominal Periclase zone, and they represent the overwhelming focus and flux of fluid flow here. So I've just given them more importance here. So again, we could play around a little bit here with fluid flux. Okay, so let's go on to the carbon isotope front here. And so here, again, what I've done is I've superimposed a couple model profiles, 1D model profiles at 2 values of the diffusion dispersion coefficient here. The steeper one here at the lower dispersion value, might be a little better fit here to the low delta C13 values here. That's in contrast, the value of 2 times 10 to the minus 6 meters squared is the one that seems to fit the oxygen profile a little better. So there's a little bit of a difference here. But I think the important thing is regardless of what curve you put through here, they're going to have high values of the diffusion dispersion coefficient. So the dispersion here is quite significant. Okay, so in both of these cases, we've interpreted in previous years that in previous publications here that the dispersion here that we see both in the carbon and the oxygen front is the result here of permeability heterogeneity that's introduced by bed-to-bed variations in the permeability. And we see that. I'll show you some information here in a bit here. Now, the 1D models they can't show you that two-dimensional structure here. Two-dimensional models have been made by folks like Goodes and Baumgartner and Persson here a few years ago. And what they did was simulate I can actually go back to the oxygen front here. And their conclusion was that, yes, indeed, there's a very significant vertical permeability heterogeneity that has to be in the system to produce this kind of dispersion, and confirming what we said as well. Okay, so the separation of the oxygen and the carbon fronts is a function of the mole fraction of CO2 that's in the infiltrating fluid. So we looked at that. So what I've shown here in the bigger front profile here is the oxygen isotope profile with distance here, with a couple of the solutions for the different fluxes that match the two center points that I've estimated here of 350 and 410. And in the back here is the carbon profile. So now, in order for the two different fluxes that match these two different center points for the oxygen profile, in order to duplicate the carbon center point here at about 100 meters from the contact, that requires different mole fraction of CO2 in the fluid. So if the center point of the oxygen front is at 350 meters, and the infiltrating fluid needs a XCO2 value of about 0.08. If it's at 410 meters, if they're further separated, the mole fraction of CO2 in the fluid can be smaller here at about 0.06. Okay, so now these mole fractions are low, and so that's consistent then with these fronts being formed by the infiltration of water-rich fluids. These values, however, are a bit higher than what Steve Cook and I estimated for infiltrating fluid based on applications of calcite dolomite thermometry to the Pericles reaction, and those values we estimated to be about very very water rich, 0.04 or even less here. So there's some inconsistencies here. Okay, so this is what goes on here at the large scale. We get significant dispersion then of features that we see. Okay, at the bedding layer scale inside the Pericles zone, then we have interbedded Pericles and four-strike calcite marbles here, and we see very large bedding-controlled variations in the oxygen and carbon isotopic compositions. We'll see that here in a moment. And there'll be steep gradients that are coherent at these boundaries. And the bedding interiors are pretty homogeneous in their oxygen and carbon isotopic compositions. And that implies that on the scale of an individual bed here, the permeability is pretty constant. So let me just go quickly through a few of these plots here. So this is a traverse inside, a stratigraphic traverse inside the Pericles zone here, where I've just measured delta 18 and delta C13 as a function of stratigraphy here. And what you can see here is that there's significant delta 18 and carbon isotopic variations that are largely bedding controlled here. And the yellowish bands here are the Pericles bearing layers here, and they of course consistently have the very lowest oxygen and carbon isotopic compositions. So when you go to boundaries here, you can see, for example, right here at this boundary here between what I labeled layer 8 and layer 9, there's a significant variation in oxygen and carbon isotopic composition. So here, the next couple of things, I'll just show a couple of one example of this, actually from the layer 8-9 boundary here. So I've plotted the delta 18 value against the distance here across the boundary here, and so you can see there's very pretty homogeneous delta 18 values within the interior of the Pericles bearing layer here. Can't quite see that so well here in 8, but if there's more data, and it's pretty homogeneous within 8 as well here. Then you see these very steep coherent, oops, there we go, coherent gradients here at the layer boundary that are just displaced slightly from the layer boundary here. But again, very coherent. So that means that these are going to have pretty low values of dispersion. And the actual value depends a bit on the kind of model one picks here. But if you pick a fixed boundary model here, you get values here of the diffusion dispersion coefficient here of much lower here, 10 to the minus 12. If you use a uniform flow model, you get something even lower here. So these are much lower diffusion dispersion coefficients here at the smaller layer boundary scale. Okay, and so here's the carbon profile. Something very similar. Constant homogeneous compositions within the layers, a steep coherent gradient at the layer boundary that's very slightly displaced from it. And again, you would get, I'll just show one of these, you get very low values of the dispersion coefficient here. Okay, got a few minutes here to show you some observations here on the Periclase reaction front. So normally the Periclase front is a fairly narrow front, but there's a certain ate where there are some unusually thick, pure dolomitic marbles, and in those areas, the Periclase and the dolomite marbles interfinger here at centimeter to meter scales. The boundaries between the layers are pretty sharp. I'll show you in a second. This replacement seems to be fracture controlled at this scale here, and so I think in this case the heterogeneous permeability of these marbles is a result of heterogeneity in the fracture density within the dolomitic marbles. So just to quickly show you a couple of pictures here. So here's an outcrop. The buff color, darker things are the residual dolomite. The lighter, whiter zones here are the Periclase marbles. And then if we get closer, so here we see Periclase marble thinning along what's a fracture set into the darker dolomitic marble here. Here's a closer vision of that. And so here you can see these are, these are coming down to thinning fracture tips here. Here's a tip of Periclase penetrating and replacing out into the dolomite, and there's an even thinner one here. And this actually continues. You can't see it very well here. It continues off to several centimeters beyond there here. And I think there's some other examples here, but I'm going to just stop here. And here's one that shows a rather complicated distribution of these that to me looks like fracture controlled here. So in conclusion here, the carbon and oxygen isotopic exchange fronts in the Alta aureole exhibit significant dispersion at the aureole scale, and in contrast, that dispersion is significantly lower at the individual bedding layer scale, as indicated by relatively constant compositions of the materials within the layers and the presence of these steep coherent gradients at the layer boundaries. I'll skip this one. The dispersion of the isotopic exchange fronts at the aureole scale, we think, is the result of significant bed-to-bed variations in permeability, reflected by significant bed-to-bed variations in the oxygen and carbon isotopic compositions. That leads to permeability and isotropy. Finally, with the exception of these fracture-controlled dolomitic marbles, these individual layers at the layer scale seem to have relatively constant permeability. And finally, permeability, heterogeneity, and isotropy in these marbles are scale-dependent. So thank you.
Thanks, John. I'm afraid we don't have time for questions. I'm sure John will be happy to answer questions afterwards. We need to keep things on schedule here. So our next speaker is Dave Pattison, and he's going to be speaking about equilibrium and kinetics in metamorphism. Just give us a minute to switch computers here. So,
looks like it's running out of juice.
If you prefer, I have one that I just loaded up with batteries.
Yeah.
You can try that one.
Okay.
And then we'll have the keyboard here, and you can use the arrows or the mouse to
Sure.
advance.
It's the first page there. Yeah, it's the first page. Here. All right. Well, good afternoon, everyone. What I'd like to talk about this afternoon is what I think to be one of the most interesting, but at the same time challenging problems in metamorphic petrology, and that's understanding the interplay between equilibrium and kinetics in controlling metamorphic processes. This is a diagram of the metamorphic facies from Frank Spear's Big Blue Book. The metamorphic facies provide the fundamental underpinning for the equilibrium model for metamorphism. And that's based on the idea that the reproducibility of mineral assemblage sequences seen worldwide and the predictable relationship between bulk composition and mineral assemblage would be pretty well impossible to explain if this didn't pertain. That said, whether the equilibrium model pertains at a finer scale, such as during the evolution of a metamorphic rock through its PT history, this is the idea of the series of continuous equilibrium states, I think that's more of an open question. So what I'd like to do is to show a few examples where I think there's petrological evidence suggesting that the equilibrium model doesn't always pertain at this fine scale. The first example, which I don't claim occurs in all situations, but I think is occurring in these examples, is the prograde unreactivity of porphyroblasts when they're reactants in subsequent reactions. So for these panels on the left, these show garnet storolite-bearing schists, and one can see that the garnets are quite idioblastic here. If you take the compositions of these rocks and prepare or calculate an equilibrium phase diagram and look at the expected reaction history for any reasonable PT path, the garnet is predicted to be a reactant in the formation of the storolite. But I think in these examples, there's no real evidence for very much, if any at all, dissolution of the garnet. A complementary example is shown over on the right here. This is a pair of samples showing storolite and andaluzite and storolite and kyanite. And in both of these situations, if you were to calculate the equilibrium phase diagram and look at any reasonable PT path to get up the kyanite field, you would predict that storolite would be a substantial reactant according to the equilibrium model in producing the aluminosilicate minerals. And again, I would argue in these cases there isn't the evidence for that. So whatever formed these porphyroblasts, I think they had to have occurred by reactions which are different than what you would interpret from straight interpretation of passage through an equilibrium phase diagram. Another example is the observation of overstepped or out-of-sequence reactions. And perhaps the best example of this is from the Bushveld complex studied by Waters and Lovegrove. And what they did was in some very special peelite samples, they looked at the beautiful record of microtextures preserved in the rocks, which allowed them to construct the sequence of porphyroblaст consumption and growth. And the results of that study are shown in the upper left. This is mode versus increasing temperature and time. And this shows a record of their interpretation from the microtextures of the consumption of the reactant chloritoid and chlorite and the growth of storolite, andaluzite, cordierite, and biotite. So the next step they did was to take the bulk composition of the rock and calculate an equilibrium phase diagram, which is shown in the lower right. This is an isobaric TX diagram here. And for the bulk composition of interest, which is between the dashed lines, they could predict what the modal changes would be going up grade. And the result of that was this mode versus temperature diagram. And without going into the details, one can see that the configuration of this diagram bears no resemblance at all to what was actually observed in terms of the interpretation of the microtextures. So their interpretation was that the reactions which led to the observed mineralogy were both out of sequence and in some cases quite substantially overstepped. They interpreted these reactions, these chlorite-consuming reactions, to have proceeded instead of the predicted reactions in red here. A comparable example comes from the Nelson contact aureole in British Columbia. This map on the left, this shows the distribution of mineral assemblages and isograds based on those. If you take the average composition of the peelites in the contact aureole and calculate an equilibrium phase diagram for it and ally that with a thermal model, one can predict the sequence and spacing of the isograds. And that's what is shown on the right-hand map. And you can see that there are some differences between the two. Two of the main differences relate to the predicted presence of the garnet zone here, which is in fact absent in the natural setting, and also the predicted disappearance of storolite, which instead of occurring just a little bit upgraded where andaluzite comes in reality is observed to occur well upgraded the sillimanite zone. So again, this would be an example of, in one case, an overstepped, and in the other case, an out-of-sequence reaction. So accepting that these might be examples of disequilibrium and overstepping, one interesting question is whether there's some way in which one might be able to predict situations in which overstepping is to be expected or not. And this brings me to the topic of the macroscopic driving force for reaction. I would argue that this, the rate at which this macroscopic driving force for reaction builds up with overstepping does allow predictability as to the behavior of these in different situations. I've described this macroscopic driving force as a reaction affinity. This reaction affinity is a term that's used in different ways in different situations, but in the context of overstepping, the way I'm using it is the Gibbs free energy difference between the stable but the not yet crystallized products and the metastable reactants. So that's illustrated in this series of diagrams. This is a schematic illustration in PT space of the Garnet in reaction. So we've got our muscovite chloride reactant assemblage here, and then Garnet's produced up here. If we overstep that, that can be understood in terms of this GT diagram. So this is the GT surface of the reactant assemblage, and this is the GT surface of the Garnet-bearing product assemblage. And where those two intersect is the equilibrium position of the curve, which is the black line up here. Now, if the reaction does not go as expected, if there's overstepping, then one extends along this dotted line along that metastable extension, and then eventually, once a reaction goes, then the system drops back down to the stable configuration. But in the intervening overstepped interval, you can see that the difference between these two lines gets bigger and bigger, and that energy difference is the reaction affinity. In situations where there is thermal overstepping, the reaction affinity is simply equal to the temperature overstep times the entropy change of the reaction. If you look at an ordinary phase diagram, there's no indication of these differences at all. So this is an example of a P-light phase diagram, 2 to 5 kilobars, 500 to 650 degrees C. This is a map of the minimum free energy configuration of the system, but there's no indication as to the relative energetic differences between, say, adjacent domains on either side of one of these mineral in or mineral out lines, or indeed of competing configurations. So there's nothing that would kind of give you something to predict as to where overstepping might be important or not. If you take the numbered reactions from this previous diagram and actually calculate the rate of buildup of reaction affinity with overstepping, you get this graph here. So this is a reaction affinity in joules per mole of oxygen in the porphyroblast on the vertical axis, and this is temperature overstep. And you can see that there's a big range of slopes here, with the highest entropy reactions having the steepest slope and decreasing down to low entropy reactions, which are at the bottom here. And this broadly correlates with the amount of water that's released in the reactions. The consequence in terms of overstepping is that if there's some sort of an arbitrarily illustrated energetic threshold for nucleation and growth, which is shown by this dashed line, then the amount of overstepping for a high entropy reaction here is going to be less than for a low entropy reaction. So I've taken these curves and color-coded them. So the highest entropy reactions are in red, these are intermediate in green, and lowest in blue, and put them back onto the phase diagram here. So you can see that there's this big red band here. This basically corresponds to the consumption of chlorite, which disappears over a fairly small interval and is a very high entropy reaction because it releases so much water. This green one here is the muscovite quartz breakdown. This is the chlorite to garnet reaction, which is not quite as highly entropic as these ones, or at least the unit entropy change isn't as big because it occurs over a much bigger divariant interval due to iron-magnesium exchange. So the next thing you can do is actually make reaction affinity maps, which show graphically the amount of overstepping, or rather the rate of buildup of reaction affinity, which allows you to predict amount of overstepping. And I've shown 3 examples here, or I'm choosing 3 examples. This is the chlorite to andalusite reaction. This is the staurolite to andalusite reaction, actually just down here. And this is the andalusite to cordierite reaction. And these are kind of the extremes. And these are the reaction affinity maps. So you can see that there's a color variation from low amount of reaction affinity to high. And I've put some contours on here to accent the differences between the three reactions. So this one is the chlorite to andaluzite reaction. It's a high entropy reaction. This is the chlorite-free staurolite to andaluzite reaction. And this one down here is the andaluzite to cordierite reaction. And you can see that the rate of buildup of reaction affinity is dramatically different between the three. And the prediction in terms of overstepping is that this one should give the least overstepping because it builds up the energy needed to overcome the kinetic barriers to reaction most rapidly. This one is extremely low to the point where possibly it doesn't happen at all, or if it does, it might be very strongly controlled by kinetic factors. The question is whether these predictions are actually observed in nature or not, and this is actually quite a difficult thing to get a hold of, but I've attempted to do that here with a few studies. I divided these into regional studies in R, contact metamorphic studies in C, and these ones are regional contact metamorphic settings. This would be like regional andaluzite sillimanite sequences, or particularly large contact aureoles like the Bushveld complex. I'm looking at 4 different types of reactions along the bottom here. These are low temperature, non-chlorite consuming porphyroblastic reactions. These typically occur in aluminous bulk compositions. Here's the chlorite to garnet reaction. This one, or this set, is chlorite to either cordierite, andaluzite, or staurolite, which is the highest entropy reaction. And then this last one here is the staurolite to andaluzite reaction, which is a low entropy change reaction. So first of all, this is the predicted position of where these reactions would take place, assuming they obeyed perfectly the equilibrium phase diagrams calculated for them. And basically, you can see the temperatures increase from these are green schist facies type reactions up to this one here, which is predicted to occur in the amphibolite facies. So the next thing is to plot where in these studies the reactions actually took place, and that's the red dots here. And overall, you can see that there is a larger separation between the blue and the red for these low temperature non-chlorite consuming reactions. The amount of overstepping implied here is about 60 to 80 degrees. For the the chlorite to garnet reaction, it's a bit variable, but overall it's a little bit less than for this one, though there is some variation. For the high entropy chlorite to cordierite andaluzite staurolite reactions, the interval between predicted onset and actual occurrence of the reactions is the smallest. And then for this staurolite to andaluzite reaction, even though it occurs at higher temperature, there's another fairly significant gap, which I would attribute to the low entropy change of that reaction. One other thing that's kind of interesting about this graph is you can see there are an awful lot of dots which line up around here at the 550 degree temperature line. This generally corresponds to the chlorite out reaction, which is this interval of very high water production and high entropy reaction. And this basically is the dividing line between the green schist facies and the amphibolite facies. So I think an interesting outcome of this, coming back to the metamorphic facies diagram, is that it seems that the greater degrees of overstepping is for these lower entropy change reactions, which appear to occur within the intervals between the boundaries between the metamorphic facies. And at least in the green schist amphibolite facies transition, this is tied to this very high entropy change reaction involving chlorite. But I would speculate that perhaps the same thing could be said for this is the muscovite quartz breakdown as well. So what I take from this is that the consideration of both the equilibrium treatment of metamorphic assemblages, but also these kinetic effects are important to at least consider when we're looking at our metamorphic samples. Thank you.
Thanks, Dave. I'm afraid we've run out of time, so we have to move on to the next speaker. So our next speaker is Veronika Hamalova, and she's going to be speaking about diffusive fractionation of lithium isotopes in olivine grain boundaries.
So I've decided to amend my title slightly to read Diffusive Isotopic Fractionation of Lithium in Polycrystalline Olivine instead of olivine grain boundaries. So diffusive isotopic fractionation occurs because the lighter isotope usually diffuses a bit faster than the heavier isotope. The relation to describe it is seen here, where D is diffusivity, M is mass, 1 and 2 denote the two isotopes, and B is the fractionation factor. So as the difference between the two diffusivities between the two isotopes increases, so does the beta value. What diffusive isotopic fractionation usually looks like is shown on the right here. So here we have concentration and 7 lithium divided by 6 lithium as a function of distance, where 0 is the distance, 0 is the point of the original interface between the high concentration side and the low concentration side of the diffusion couple. So as lithium diffuses from the left side to the right side here, a greater flux of lithium-6 will move over to the right side, and so that will cause an overabundance of lithium-6 just to the right of the original interface, and that will decrease the 7:6 ratio. Since so much lithium diffused out of the left side of the diffusion couple, this will sort of cause a deficit of lithium-6 on that side, and so there the ratio increases. So what you end up with is these two little bumps, one positive, one negative, and the amplitude of those bumps depends on the beta value. So the beta value can range from 0 to 0.5, and as you increase beta value, the amplitude of these bumps increases. So here, from blue to green to red, the beta value is increasing. So for lithium, beta values have been measured in aqueous fluids, silicate melts, and single crystals. So in aqueous fluids, it's about 0.015, silicate melts about 0.2, and in single crystals, it's about 0.3. So what about diffusive isotopic fractionation in polycrystalline rocks? So in this case, the lithium would diffuse both through the crystals and the grain boundaries. One instance where this may be applicable is when a oceanic slab is altered by seawater. This increases its lithium concentration and its delta-7 lithium value. As the slab subducts, both the lithium concentration and the delta-7 lithium value decreases as lithium is partitioned into the fluid phase during dehydration reactions. But whatever lithium is left in the slab further subducts and then is free to diffuse out into the mantle. So the question then is, how long does this lithium isotopic heterogeneity survive at mantle temperatures? So one way to shed light on this issue is to look at the altered subducted slab and the mantle as a diffusion couple. So this is one such example of that by Vlastilik et al. So in this graph, we see delta-7 lithium as a function of distance from the center of the altered oceanic crust, and the crust-mantle interface is shown by the dotted vertical line. And so these authors conclude that after 1.5 billion years, there's still a lithium isotopic heterogeneity that is able to survive that long. So what these models are very highly dependent on is the diffusivity of lithium that they input into their models, as well as the beta factor. So that's what we set out to find. So our experimental setup consists of 2 steps: a rock synthesis step, where powdered natural olivine or synthetic olivine is packed into either an iron or nickel capsule. That capsule is then that capsule is then run in a piston cylinder apparatus at 1100 degrees from 1 to 1.3 gigapascals from about 12 to 24 hours. And there's always a minor phase included, like pyroxene, which controls the grain size by grain boundary pinning. So after this rock synthesis step, the capsule is sectioned perpendicular to its long axis, and that cut face is polished, and then that cut face is juxtaposed to a lithium source, in this case spodumene. So then the diffusion experiment is run at the same conditions as the rock synthesis step, except for shorter amounts of time. After the diffusion experiment, the capsule is then cut perpendicular to the interface between the source and the polycrystalline matrix, and is prepared for analysis by quadrupole ICP-MS or ion probe. So this just shows some of the results that we have so far. So on the left here, you see normalized concentration as a function of distance. So this is 0, this is 3,000 microns. So you can see that the concentration decreases in error function style. And when this is, this gives us a value of about 7 times 10 to the negative 12 meters squared per second. So this would be the effective diffusivity, and just what I mean by effective diffusivity is just it's the combined effects of the lithium diffusing through the crystal lattice as well as the grain boundaries. So this is compared to diffusion of lithium in a single crystal of olivine by the vacancy mechanism, which gives values about 10 to the negative 14 to 10 to the negative 16 meters squared per second. On the bottom graph here, we have the 7 lithium to 6 lithium ratio, again, is plotted as a function of distance. And these are our quadrupole results, so the errors are about 2 sigma, and they're quite large, but nevertheless, you can see a decrease in the values until it jumps back up to the background concentration of the olivine. Up here in the top right, we have our first ion probe analyses data. So this is the scale bar here. This is 300 microns. So this time the lithium source is on the right and the polycrystalline olivine is on the left. And so we had 2 spots analyzed really close to the source and 2 spots analyzed far about 1,500 microns away from the source. And so the 2 spots close to the source yielded a delta 7 lithium value of about plus 30 per mil, whereas the one further away from the source yielded a value of about negative 22 per mil. So very large fractionation over a very short distance. Most of the experiments have been giving us beta values of about 0.1 so far. So this graph here just compares the beta values that have been found for lithium so far. So again, we have aqueous fluid, silicate melting crystal, and polycrystalline olivine sort of sits in between aqueous fluid and silicate melt. So now I'm just going to show you some results of modeling that we've been doing to try and figure out where this fractionation is occurring. So what the model space looks like is basically a source with a single straight constant thickness grain boundary perpendicular to that source. So this is very similar to the Fisher and Whipple-Leclerc type models. And the rest of the model space is crystal lattice. So the diffusant here can either jump from the source directly into the grain boundary or from the source directly into the crystal lattice. And it could also jump in between the grain boundary and the crystal lattice as long as it maintains partitioning equilibrium. So the user inputs are 2 diffusivities for lithium-6, one in the grain boundary, one in the crystal lattice. The same thing for lithium-7, and a partitioning value for both isotopes and time. So the good thing about this model is you can control where the fractionation is occurring. So if, for example, you would only like isotopic fractionation to occur in your grain boundary, then you would set the diffusivities of lithium-6 and lithium-7 in your crystal lattice to be equal, whereas in the grain boundary they would be different. So these are just some of the results for when the grain boundary is many orders of magnitude greater than the diffusivity in the grain boundary is many orders of magnitude greater than the diffusivity in the lattice. So this would be sort of equivalent to a low temperature type of experiment. So in both of these graphs, we have lithium-7 over lithium-6 plotted as a function of distance away from the source. And the difference between the 2 graphs is that in the left one, fractionation was only allowed to occur in the grain boundary, whereas in the right one, fractionation was only allowed to occur in the lattice. And once again, we have from blue to green to red, we have an increasing beta factor. So here you can see that when grain boundary is allowed to do the fractionating, then the dip that we've been seeing before is produced, Whereas when the lattice fractionates only and the grain boundary does not, that's not produced. So what's kind of not shown in these images is the fact that when the grain boundary is so much higher than the grain boundary diffusivity is so much higher than the diffusivity in the lattice, the grain boundary really sort of holds the dominant role in determining what the isotopic composition of the lattice is at the end of the model. So that's when the grain boundary diffusivity is much higher than the lattice diffusivity. If the grain boundary diffusivity is about equal to the lattice diffusivity, which is sort of equivalent to a high temperature environment, let's say, similar to the temperature at which the experiments have been run, then the grain boundary loses its dominant role in controlling what the lattice isotopic composition will be. So the reason why this happens is there's so much diffusant that's being sort of lost to the lattice that the grain boundary diffusivity is basically equal to the lattice diffusivity. So some future directions that we want to do is we want to do some more lower temperature experiments to draw out any isotopic fractionation occurring in the grain boundaries, and also some higher temperature experiments to better simulate mantle conditions. Thank you.
We have time for a question or two, if there are any. Serena?
Okay, I didn't quite hear all of that.
I had a hard time hearing as well.
So did you mean you mean in this here? Okay. Right, okay. Okay. Yeah, so you're saying the concentration of lithium in the source is very high in our source. Small. Okay. I'm not sure I understand your question. Can we talk about it later?
Yeah, I'm going to encourage you guys
Yeah.
to talk about this later because we need to move on. Thank you.
All right, thank you for your patience while we work through the technical issues. The next speaker is Costa and Mazanev, and the title is A Case of Alzheimer's Disease in Magmatic Crystals.
Thank you, and thank you the organizers for organizing this session and inviting us to talk to you about this. I guess this is image which kind of made me thought about what I could talk here. I mean, this is an olivine crystal. It's an olivine crystal from a volcanic rock. And what you see here is a phosphorus map. So it's just concentration, relative concentration of phosphorus. And what you see here, it's a very, very unique type of features in the sense this shows that this crystal has started growing skeletically. I mean, this is a very different image from the one I'm used to look when I typically look at iron, magnesium, or nickel concentrations in olivine, and made me wonder, what's going on? And this olivine has seen a history that I've never seen before. So this kind of triggered my line of thought. And in this presentation, maybe we'll look at, can we do something by looking at this phosphorus zoning and these older histories of the crystals? Can we recover the kind of past history of the crystal that we typically don't see if we use other elements like iron and magnesium? And this looking at these crystals and understanding the processes and the timescales is useful for different ways. I mean, there's kind of a lot of more new studies that have been doing now to look at the timescales of this that are occurring in these volcanoes. And for example, because one would like to relate them to what's going on in seismicity, and here are two recent studies where people have looked at the zoning in crystals, zoning in pyroxenes or zoning in olivines, and trying to relate this to the seismicity of the volcano, and this way trying to understand the processes. The timescales, however, of these types of studies are always pretty short, and here's a compilation of the literature that I just did recently. We have, for example, olivine. Most studies get timescales of about less than 100 years. Plagioclase, you have a larger range, up to some thousands of years. And here you have, for example, titanium in quartz could provide you long timescales, but at the same time, there is lithium in quartz, which give you also very short times. So although there is a spread on timescales, I would say most of them are less than 100 years. And the question is this real? I mean, is this reflecting that all these magmatic processes are always occurring in less than 100 years, or is it a bias of, for example, the elements that we're using to measure these processes? So this could be one of the things are limited by the restricted range of variables, and a kind of back of the envelope calculation would be this one, for example, where we have equilibration of a crystal in 3 dimensions, is a kind of ideal phenocryst, if you want, of these sizes, where we have calculated how long it takes to nearly fully reequilibrate these different elements, and here's a blow up. And for example, if you want 90% of reequilibration of magnesium in plagioclase, you can do this in a few years. Forsythite in olivine, you can do it in a few hundreds, and then plagioclase, strontium, it would be similar, etc. So it shows that in a few hundred years, you could completely homogenize some of these elements. So the idea is, okay, what can we do with these elements if they're completely homogenized? And what we can do is look at other elements, notably here we're talking about phosphorus, that do not diffuse, that diffuse much slower, and use this to understand, to get more informal, more reliable information about the growth history, initial conditions, and also hopefully at the boundary. This presentation will focus mainly on this part. We have started to work with this part. I'll show you at the end some of what we have started to do. But mainly would be the growth history. We'll use as a case study the volcano in Chile, Llama volcano. And we'll use mainly olivine because we know diffusivity is relatively well, we know thermodynamics relatively well, and so it's easy to study. Before I go into this, I also want to stress that to do this type of study, you have to know what you're looking for a little bit. You cannot just take a crystal and isolate it and just make the whole story out of this. So here I'll give you the introduction for the Llama volcano, conceptual model of Llama volcano that has been worked out by Caroline and co-workers, where we have this relatively active volcano. It erupts every few years. And they have this model where you have intrusion of basaltic magmas. They're relatively crystal poor. They reach this level where it's already a crystal-rich zone. They interact, and then they basically proceed. So we have basically three sort of stages, or three sort of stages that we can keep in mind for interpretation of the crystals. Some examples of these Llama crystals. This is phosphorus maps. You can see this is skeletal growth here, very different zoning from what we see on iron and magnesium. And this is the crystal that will be working most. You see this thing, these high phosphorus zones here, and you have here melt inclusion showing that this was probably showing fast growth and entrapment of inclusions, and then followed by kind of a quiet period and some oscillatory zone, and finally some dissolution also. I also would like to stress that for sort of in other people that have started looking at this phosphorus zoning, this is a very nice publication where kind of opened my eyes. I've looked at these olivines, you're not seeing the whole story, and also I remember a presentation from last year at AGU that we're also showing this. So it's a common feature that these olivine crystals may show this. So here we have, this is our olivine crystal, this is a reflected image, this is a magnesium map, and as you see here, you can contrast, this is this map here, you can contrast the difference on features if you look at the phosphorus versus the magnesium. So what we did here is we used a laser in the scan mode, this is in ANU, and so here you see the scans, so we use the laser and you continuously scan, and you get these are the profiles, forsterite, calcium, nickel, chromium, phosphorus, and aluminium. You can see this is not as sexy as using an ion microprobe. I mean, you have here a lot of noise, and it's not as good, but still you can see the profiles, the trends relatively well. And basically you see, I mean, I see two main features, which is this, I was showing you this high phosphorus zone that occurs in the core next to the skeletal part, and aluminium doesn't seem to care. Chromium might care, it's kind of decreasing. Forsterite, calcium, and nickel, they don't care. So the idea might be that maybe more than one of these elements was showing a similar zoning, but because of the diffusivities which are like this in olivine, these elements have re-equilibrated. So that would be the first thing that we will look at. And the second one is also this part. You see that the crystal is reversely zoned, so forsterite going towards the rim. This is showing this replenishment event, more mafic magma coming in. You see it also in the nickel. Chromium is more complicated. You have some down and then up. Apparently this correlates with some high phosphorus here, which we'll not look in detail, but it's also happening. And basically, just to stress that the chromium is doing a little bit something different, but if you look in detail, though, you see also two slopes. I mean, here's the one slope and here's another one. So it seems that there are two events that are also happening in this rim, and we'll look at the end about these two events. First, the phosphorus. So how one can think about it, I thought about it by using some equations for the disequilibrium growth, and the first thing one needs to do is to normalize. So you have to find how in disequilibrium is disequilibrium, and what I did is I took the kind of flat or low phosphorus zones as my equilibrium values. I assume that here the crystal was growing at equilibrium, and then just normalize it to the rest. So you have here, this is now a reverse plot, but you have here the high phosphorus zone. So this high phosphorus zone was enriched 7 times its kind of equilibrium concentration. And with this we can do something. We can, for example, we use a growth plus diffusion equation, and we can take the analytical solution of Smith et al., who has been around for quite some time. And what we need to plug into this equation is the diffusivities of the elements in the melt, which gives here some values. Phosphorus is about as low as aluminum, relatively slow, and iron, calcium, magnesium are faster. So there's some values here. We also need to know the partition coefficient, and you have here the lowest partition coefficient is aluminium, then calcium, phosphorus, and nickel is compatible. So basically these equations say that these elements with the slowest diffusivities and with KDs that are farther away from 1 will be the ones that are potentially showing more of this kinetic effect. So if you do the model, this is what you get. This is distance from the rim, or not from the rim, but from the moment that the crystal started to grow at this rate. And what I was trying to achieve is that at about this distance, sort of 20 to 40 microns, we have an enrichment of phosphorus, which is a maximum, which is about 6 or 7. So this is a kind of a plot of a fit of the phosphorus maximum. And this, for doing this, we require this type of growth rate, which is relatively fast. Another interesting observation here, it would predict that the model predicts that the aluminium would be even more enriched, and we'll come back to this. Calcium, not so much because of the partition coefficient also, but all diffusivities, and nickel, it would be a little bit depleted. Related calculation would be, okay, what type of growth rates we need if we don't want to have kinetic effects. So I say, look at my crystals, I believe nothing is affected by kinetics. Then when you say this, you are implying this kind of growth rate, which is about 2 orders or 3 orders of magnitude slower than the other one. Okay, so kind of conclusions, this would be, or part of partial conclusions, is this phosphorus enrichment requires these types of growth rates, and basically it means that this core grow in 10 minutes. Okay, so I think this is showing that there was a quenching. So you have the magma, it's hot, moves from one part of the deep part and goes to the upper reservoir, and then it quenches and you grow these high phosphorus zones. As I said, the high aluminum should be more enriched, but high aluminum is a measure element. So if you want to multiply by 2 your aluminum content in the melt from whatever 15 to 30, there's no way this is going to happen. Particularly because you have to conserve mass and charge, and so you have to start thinking about the multi-component diffusion. Basically, the aluminum will not enrich so much if silicon doesn't allow him to do it. So I guess would say this shows the model is for trace elements, not for measure elements. So that's, I guess, okay that we don't see the enrichment in aluminum. And as I said, yeah, the rest of the crystal grew at much slower rates. So now I want to make a little bit of a transition, because here, so this is what happens with the disequilibrium model. But then if we think of the context, so you have this magma with this high temperature, it arrives, it quenches, and then the growth rate decreases. And because of the Forster rate also is changing, it implies that the high temperature part, the high phosphorus high temperature part grew from a melt which was more mafic, so the Forster rate would have been higher. And this is what we will kind of look into this, and we'll look into this by using melt. So basically we've taken melts, we've calculated the liquidus for these rocks, and we calculated the compositions of the olivine in equilibrium with these magmas, and then from there we have a temperature olivine plot, and from there we can assume a given time and temperature evolution, and then we can see if this fits what we have been doing. So again, stressing here this, you remember this simple scheme, 1, 2, 3. So here we have 1, we have arrival of this mafic magma. This mafic magma quenches, and it stays at a given lower temperature. And then before eruption, there's a replenishment, and this temperature rises up. So this is a time temperature plot, which I agree it's arbitrary to some extent, but I think that the 3 steps, sort of hot, cooler, and hot again, it's robust. And from here we can calculate that would be the olivine in equilibrium. So if we go at this temperature, this would be the olivine in equilibrium. If we go at this temperature, this would be, and this should be we think it's this plateau. I mean, I see now there's a little bit misfit between this plateau and this one, but this it doesn't matter. I mean, we just have to stop at lower temperatures. So, I mean, higher temperatures, because what we want is to have a plateau here at 74, which is this plateau here, and then this 79, it's basically, well, it's a little bit also higher, so it should be about here. But that's what we're trying to fit, basically. We're trying to fit that this plateau here should have grown at this temperature. This is what Mel says. It doesn't say when, but it just says that it should have grown at this, at this temperature here. And then this part would be growing here. So if we do this, then this is a zone that would be the high Forster zone, because this is a high temperature, and this is the size of this is constrained by the size of the phosphorus. This is the low temperature zone, low temperature olivine. And then at the end, you have high Forster again, and these things goes back again because you have replenishment of another magma and then the eruption. So if we do this, it's a relatively simple model to do now at this point. We see that to eat out a part like this of Forsterite, you need at least 6 years. So you could have taken more, because since you are calibrated, it means you started at least 6 years, it could be more. And to fit this with just one single intrusion, you need 1 year. So we see that from this, we can say that this crystal had a history, an older history of at least 6 years, maybe more, and a last period here that was basically doing nothing, so 5 years, and the last event of 1 year of reheating. A little bit quicker, so this can be done for other elements. For example, let's assume that the chromium also show this. This would imply 200 years, so this core would have been at least around for 200 years. And also, we'll quickly look at these things at the boundary. There's basically 2 slopes here. So we've done a relatively more sophisticated calculation. There's a little bit of animation here where we simulate 2 replenishments. There's, first 1 replenishment here, then constant temperature, another replenishment, and we check how the concentrations change at the boundary. And so basically, you're moving the temperature here, and then the Forsterite is going, and then when the thing kicks up, this goes back up again. So this is to show basically that we can try to, I mean, if you look at these profiles, if you measure this, you probably do a single fit of this. You will not identify 2. And the same thing for chromium, particularly for our laser data. I don't think we would be able to tease out some of these complexities, but hopefully we'll be able. So I remember some years, quite a few years back, there was somebody trying to explain the Himalayas, the study of Himalayas with a single potassium feldspar. So here I think I'll be more modest. I'll just use one olivine crystal to explain the story of this volcano. And basically, we have 4 steps: fast quenching, about 10 minutes, this at a quiet period, at least 5 years, this zone, which we don't know exactly what to make it. Probably there's 2 intrusions here, less than a year. And finally, this solution. And thank you.
I'm afraid we don't have time for questions, but I encourage you to contact Fidel outside this session and follow up with him there. I'll introduce the next speaker.
So, sure, go ahead.
The next speaker is Marshaw, and he's going to be talking on differential diffusion in rutile, disequilibrium formation of the continental crust.
Okay, thank you. So today I'm presenting this niobium tantalum diffusion study in rutile. And this is work that I've been doing, and it's an ongoing study in cooperation with Ralf Domen at Bochum. He's doing the diffusion experiments, most of them, and Thomas Ludwig at Heidelberg, who is operating the ion probe. And we mostly use the ion probe to do depth profiling analysis of the diffusion products. And this is now supported by NSF. And so the background is that niobium tantalum is maybe one of the most important geochemical tools that people use to tell something about the formation process, the process that formed the continental crust or differentiated the continental crust out of primitive crust. And one of the most, the 2 most significant features of continental crust, this is a trace element plot, a spidergram. The most important features are negative trough in niobium tantalum and in titanium. So there is co-depleted in those 3 elements. And the other important thing is that it has that all these geochemical reservoirs, the mantle, the more basalts, continental crust, everything has a subchondritic niobium tantalum ratio, and there has been speculation on that, if maybe niobium is in the core or is in some hidden reservoir. But more important than the overall depletion is maybe the differentiation, the internal differentiation of the silicate earth. And it's important to note that the continental crust has a lower niobium tantalum ratio than any of the other parts. It's lower than the more basalts, and it's lower than bulk silicate earth. Whereas the ocean island basalts, any intraplate magmas, have a very high niobium tantalum ratio in general. So the question is, how does that work? And usually what geochemists do is they take partition coefficients between the relevant minerals and the melt that will be extracted to explain or to model the evolution of trace element ratios in the fractionating reservoirs. And if you look at niobium tantalum, you need to look at titanium minerals, because those are the minerals that host these elements in any crustal rock or high-grade metamorphic rock. If you look at eclogites or granulites, niobium and tantalum are hosted in rutile and also in ilmenite and titanite. Here's the partitioning, relative partitioning of niobium and tantalum. And this is temperature. If niobium and tantalum would show equal partitioning between rutile and melt, they would all lie at 1. As you can see, at low temperature, that is indeed the case. So you wouldn't get any fractionation between niobium and tantalum during partial melting. At high temperatures, it's even worse. You get a preference of tantalum in rutile, and the same is true for ilmenite and titanite. So here again, it demonstrates that rutile has either this should be tantalum. It has either preference for tantalum or it's equal to 1. But we don't have any partitioning that prefers niobium. And the consequence of this is, of course, that if you have partial melting with rutile in the restite, you will either get melts that are identical to the protolith in niobium tantalum, or that are even lower, that have even higher ratio, because the tantalum would stay in the restite, and you would get melts with very high niobium tantalum ratio. So the consequence of that is this conundrum that the continental crust, which should represent the fractionated product of partial melting, has lower niobium tantalum ratios, whereas all the equilibrium melting models predict that it should have a very high niobium tantalum ratio. So all the equilibrium models have failed to explain that paradoxon. So that's why we went to as far as to question the assumption of rest-tight melt equilibrium. And in order to address that, we need to look at the diffusivity of niobium and tantalum in the major mineral host, so in rutile. And that, of course, requires experiments. Then we need to look at temperatures of partial melting, and that may start at dehydration melting of muscovite or biotite and amphibole. That's what happens in partially melting crustal rocks in this kind of temperature range. Grain sizes of rutile are important. If you look at diffusion, they typically in the range of 100 micrometers to maybe a millimeter, or even larger in some cases, in the relevant rocks. And rest-tight melt equilibration times. And these equilibration times depict the time that the melt, a partial melt, would stay in contact to the restitic minerals. It's not the time of partial melting overall. That may take millions of years in a high-grade terrain. But the amount of time that the melt has to equilibrate with restitic minerals before it's extracted into pods and veins and is extracted from the whole rock volume. There's some good work that I'm happy to point out to people. So the experiments are two different types, completely unrelated. The first type is single crystal rutile, where we deposit the diffusion source, so something titanium oxide doped with niobium and tantalum, and those are annealed in a gas mixing oven at reducing conditions at a very large range of temperatures. So we're doing experiments between 850 and 1150 degrees C. And then that is analyzed with SIMS in the depth profiling mode. So you're drilling down your SIMS spot into the crystal, and you can then determine the diffusivity. The second type of experiment is just dropping a rutile crystal into a niobium tantalum doped glass or melt then, and analyzing the product after diffusion, analyzing the product with electron probe stepwise profiling. And this is the result for the ion probe, and it's on the right side here, concentration versus depth, and that is a very striking result, I guess. You have a steep profile for tantalum and a very large profile for niobium, which immediately tells us that niobium is much, much faster than tantalum. So that opens the door to a very large kinetic fractionation of this element pair. In this particular case, niobium diffusivity is 8 times higher. This is the electron probe, so it's just sectioning the crystal and measuring profiles parallel to the C-axis in this case and parallel to the A-axis. So there's certain anisotropy of diffusion, but again, niobium is much faster than tantalum. And here's our collection of results between 850 degrees C and 1250, two different, entirely different methods, entirely different analytical methods, and they correspond very well, and you have a good determination of the niobium diffusivity. And in every single case, it's important that we determine the two elements at the same time, simultaneously. So although there's a certain scattering, every individual experiment has a very solid determination for the relative diffusivity of the two elements. So in summary, niobium is 4 times faster than tantalum. And then we take that information and look at partial melting. So we have this simple sketch here. This is a rock with a rutile crystal. You generate partial melt. Some of the rutile will dissolve into the melt until the melt is saturated in titanium. And then this is the sketch showing niobium and tantalum profiles through the rutile and through the neighboring rock. And then as the rutile has dissolved, it has oversaturated the melt in niobium and tantalum. It's like if you dissolve a garnet crystal and you get an oversaturation in manganese in the surrounding rock. And this will simply lead to a back diffusion of the highly compatible elements into the restitic rutile. And depending on your timescales, this will be a very long profile or very short profile, but at some point the melt will be extracted, leaving the rutile partially equilibrated, depending on timescale. So this is depicting the thing in detail. Here's the melt, here's the rutile crystal, this is the radius of the rutile crystal, niobium-tantalum ratio. You're starting at 14, there's bulk silicate earth value, and at very short time scales, there's a yellow line, it's a very steep profile, and with time you get longer and longer profile length, and at about 1 million years the whole thing is equilibrated. So you can look at this in a different way. This is time versus niobium-tantalum ratio, starting at bulk silicate earth value, 14 on the left side here. And for the first few months or so, there's no equilibration. It's both niobium and tantalum are too slow to do anything. So I call this the fusion, non-equilibrium fusion scenario. Then in the red area, you have a strong kinetic fractionation of niobium and tantalum. So you generate very low niobium-tantalum ratios in the melt, and then as tantalum catches up, the thing goes back, and the yellow area is the equilibrium scenario. So over 6 orders of magnitude in time, we are kinetically fractionating niobium from tantalum and generating very low ratios in the melt. So this is my global plot showing time scale on the vertical axis and temperature here. And these are the same fields as you saw before, non-equilibrium fusion. The red area is our kinetic fractionation, and only the green area is where you have the traditional equilibrium melting scenario. And the black boxes are estimates for temperatures and times of melt rest-tight equilibration in natural rocks. And as you can see, they are mostly inside the red field and not in the green field, which means a prediction is in natural melting scenarios of any rock with any rutile in the rest-tight, you'll have kinetic fractionation, you will not have equilibrium, which means you get a low niobium-tantalum ratio in the melt and not the equilibrated or the enriched scenario as predicted from equilibrium. So just to summarize this, niobium is much, much faster than tantalum. You can easily see that here. Crustal melt extraction processes will lead to kinetic fractionation of niobium-tantalum, and this will happen over 6 orders of magnitude in time. And so the assumption of equilibrium during partial melting has to be abandoned here, at least for the niobium-tantalum element pair. And I want to point out that Senator Cato is with me on this conclusion. Thank you.
We have time for one short question.
Yeah, so the question is what happens in metamorphic systems. I'm happy to come down to the Smithsonian and give a talk about metamorphic systems as well. I mean, there are plenty of applications of this problem, and you can do studies of geospeedometry and everything in a titanite rutile bearing system. I just took this example in my 15 minutes talk to apply it to partial melting. Thanks, yeah.
Okay, the next speaker is one of the invited speakers for this session, and the title is Implications of Bishop Tuff Zircon Uranium Lead Ages for Rates of Zircon Growth and Magma Accumulation by Mary Reed and Schmidt.
All right, thanks. And I can advance here. So, good. All right, well, good afternoon, everyone. I'm going to be focusing mainly on geochronology today, but I thought I'd start out by just reminding us the relationship between geochronology and things like magmatic rates and timescales. You know, from geochronological information, we can learn something about the absolute and relative timescales of magmatic processes, and we've also seen some examples, Fidel Costa's talk, using rate-dependent phenomenon to get at absolute and relative timescales. But we can also use geochronology to get at those same rate-dependent phenomenon, and from that then be able to go on and calculate again absolute and relative timescales. But those timescales can also lead back to understanding rate-dependent phenomenon. So the ultimate result is we end up with this wonderful web of information that we can use to try to get at the tempo and the dynamics of magmatic processes. And I wanted to illustrate some examples of this using the Bishop Tuff from Long Valley Caldera, and probably it's familiar to everybody in this room as being a voluminous zone silicic eruption that erupted in eastern California, or what is now eastern California, producing coeval ignimbrate flows and airfall deposits. Gil Guala and others have just recently published a paper looking at the mineral quartz from the Bishop Tuff, and they've taken advantage of the well-known variation in cathodoluminescence intensity within these quartz crystals, which can be correlated with titanium concentrations, and then use the diffusion rate of titanium to get at, again, magmatic timescales and rates of processes. And specifically what they've done, and you can see it here with the CL intensities, is they've looked at where there are steps in the CL intensity, here and here, for example, and then looked at the amount of time that's required for diffusion or relaxation of those profiles, assuming that they started out as vertical steps. And again, using the diffusion rate of titanium within quartz. And what you can see is timescales here, nearly 3,000 years here, 350 here, 29 here, as you would expect then. This boundary appears to have formed 3,000 years before this boundary here. And from that, then again, you can use the rate of diffusion of titanium and quartz to get at information like, from this we can deduce the rates of quartz crystallization. They also use the rates of faceting of melt inclusions within quartz. So here's a melt inclusion and a quartz crystal. And you can see differences in, we imagine that when the melts are entrapped initially and then ultimately freeze as glass, they have a regular shape such as this, but that over time they become faceted such as this. And they've estimated the timescales that are required to go from this more amorphous shape to a faceted shape. And again, for the Bishop Tuff quartz, 1,500 years here, 600 years here. So we're looking at timescales of several hundred years to a few thousands of years for formation of these crystals. Now, in potential support of this are the results of Crowley et al., who dated single crystals of zircon from the Bishop Tuff, and the results of those ages are shown here with two outliers that sit up in here. And they obtained an age of 767,000 years, which is an excellent agreement with the apparent eruption age for the Bishop Tuff of 767,000 years. So it appears that these crystals formed very close to the time of eruption. And interestingly enough, Fidel brought up the fact that we often see a difference between the timescales of major phases and minor phases, accessory phases, and this doesn't seem to be the case based on these data. So I'm going to refer in the rest of my talk to this tau, which is just the difference between the time of zircon crystallization as determined from the geochronology and the time of eruption, and allowing for all of the various kinds of uncertainties that come into play here. You might be able to imagine a maximum of 5,000 years for crystallization of the zircon crystals from the Bishop Tuff melts. From that, of course, we can determine a rate of magma accumulation, assuming this is giving us some idea about how long it took to get the magma together, and a mean zircon crystallization rate. Now, I want to point out the fact there were a couple of outliers here that they excluded from this mean crystallization age. So there is a hint that there might be something older in these zircon populations. And in fact, I had looked previously at this, as has Justin Simon, in two studies that we had done on the Bishop Tuff, where we'd done, instead of looking at a whole zircon, we'd done spot analyses within, on cross sections that were exposed within the zircon crystals. And what we found was some difference between the earlier erupted part of the Bishop Tuff and the later part of erupted part of the Bishop Tuff. But once you remove things that look like they probably crystallized close to eruption, it actually turns out to give a fairly coherent age of about 850,000 years, which now works out to a tau of 83,000 years as an average, so more than an order of magnitude older than what we were saying before from the single crystal results, and magma accumulation rates and zircon crystallization rates that are, of course, more than an order of magnitude lower as well. So clearly, these differences in the ages that we ascribe to the zircons are giving us some very different ideas about rates of magmatic processes. Now, I really want to emphasize the fact that these are really complementary approaches. They're giving us different insights into the system. So the single crystal analyses are really biased towards the near rim growth because that's volumetrically where most of the zircon is. On the other hand, when we go in and we expose a cross-section and do spot analyses, we're going to be biased towards the interior growth. It's very difficult to get a true rim analysis because you can't really get the spot on the rim using these approaches. Okay. I don't know. I don't think so. Yeah, it's on there. Well, so now you got the background and you can speculate. I think there's something wrong with the projector. Yeah, he's going up. What do I? Well, as I'll show you in the next slide, there's actually a lot of text, so I can give you a heads up, and then we can move through it fairly quickly. The approach that we've taken a third approach, which is to use serial sectioning, where we've oriented the zircons so that their rims are at the top of the ion probe mount, and then we bombard them with the ion beam that way. And in that way, we're able to get a rim analysis. And we had tried this once before, and I'll give you some new data showing that. And then we would polish them down to known depths and do another analysis, a sequence of analyses, so that we could actually now, rather than going across the stratigraphy within the zircon, we can look at the stratigraphy as we're going downwards through the crystal. Some of the other things that we did, we hadn't previously acid washed the samples, so we acid washed them in HF this time, which removes the glass, any glass there might be on the rim. We employed a 100 nanoamp beam as well as other times a 15 nanoamp beam. So 15 nanoamps is kind of the traditional size of the beam. We used a more intense beam in hopes of getting a better ion yield and therefore better precision. Oh, should I just give my... Are we going to
keep going?
Okay, I'll just keep going. They're not going to, apparently not going to fix the projector, so Del, we're going to get one. We'll just kind of...
They're going to replace it, and it'll take a few minutes.
Okay. Should I just keep talking for now? Or you guys all need coffee, an early coffee. Well, let me see how far I can get before I can go take you through those results pretty quickly, I think. But I put so much thought into how to present them. What else did we do? I also wanted to let you know that all of the ages are corrected for disequilibrium for the relative sensitivity factors in the ion probe, and for for common lead, of course. Very nice. Yeah, come on up. That's okay. Well, in the next slide, where you can see the rim analyses. Rims don't like to give up their ages very well. So even though we employed 100 nanoamp beams on the rims, we still didn't get the kinds of precisions that you would ideally like to get on the rims to be able to make a comparison directly with the argon-argon ages. But in fact, if you could see the slide, you would see that the data do cluster around the eruption age for the Bishop Tuff. So it does give good agreement with the Bishop Tuff, which reminds me of the one other very important variable I wanted to explain. We also calibrated, we hadn't done this previously, we calibrated our analyses or employed the 61308A standard, zircon standard, which is a 2.5 million year old standard, so very young and kind of closer in the age range of the Bishop Tuff, as an internal calibration point, just to see that we really truly are getting absolutely accurate ages. And so we were within uncertainty of the TIMS analyses on that standard, and between two different sessions where we've employed that, the numbers agree within 1%, which is, as we'll see, I hope, much better than the differences that we see in the Bishop Tuff zircons. So imagine now, you believe me, that those rims really are eruption age. There was evidence of eruption age growth. When we polish them down 10 microns, we find an age that's closer to 800,000 years. So I think it works out to about 35,000 years older than eruption. So again, at 10 microns, about 35,000 years before eruption. We actually polished them down a little bit further, and I wasn't going to show those results, get a similar age. And then when we go down to about 33 microns into the crystal, we get ages that cluster around probably about 870,000 years, so about 105,000 years before eruption. So there's a nice, in the same way we saw with quartz, a nice orderly sequence of ages going inwards into the crystals. So the challenge, and so our results really seem to corroborate the previous results that we'd got when we did the cross-sectional analyses, that there is older zircon growth buried within these crystals. And the challenge then is trying to reconcile the single crystal analyses with these the depth profiling analyses, the ion microprobe analyses. And so my last few slides show you a mass balance that I did, balancing the, trying to estimate for a given age, say 105,000 years aged core, how big could that core be mixed with a zero-age rim to produce this 5,000 year maximum age that are seen in the single crystals. And it turns out that you could have a core that's as big as 70 microns across. Yes. Oh, yay, okay. So how much should I just keep press on right on through? I'll just, okay, no, I'll just do this really quick. So as I said, sorry, I didn't mention, backwards, okay. So you know all this, but basically that's the technique we employed. The samples are from a variety of locations, so they're from across the stratigraphic sequence of the Bishop Tuff. And if you're interested, the zircon trace element data have been published elsewhere. So you already have heard about this. The tau in this case, -9 plus or minus 16. If we take out these two low values, turns out to be overlap very nicely. This red band is the ages that we get for the zircons, the mean age. Since you can see this now, again, quickly explain this. This is just showing you that these are organized in sequence from early to late within the eruptive sequence, but within each rock, I've organized them in terms of just increasing ages. And you can see there's no real evidence of a distinctive age progression as you go up through the stratigraphy. 12 microns, 35,000 years before eruption. 33 microns, 106,000 years before eruption. And you've all had a chance to look at the data. And so with the 100 nanoamp beam, we do actually get more precise ages, except on the rims, and the rims just don't seem to want to cooperate. So this is what I started to tell you about. I've looked at what could the length of the core be, assuming some maximum core tau. So if I assume that the tau is, the mantling region is 0,000 years, and I assume that I can assume that the core is, for example, what I determined this 105,000 years. We could estimate then something about the interior domain, this interior core, and how big it could be. A core of 105,000 years could be, and still preserve a single crystal age of 5,000 years. I've compared it here to the cathodoluminescence imaging of Crowley et al., and you can see that they identified a core domain within this that's somewhat smaller than the domain that's permissive by this mass balance calculation. In addition, they also found that the concentrations were lower in the cores than in the rims. And so if I allow for those differences in concentrations, I can have an even bigger core at 105,000 years. An even bigger core would be permitted, and still might not be easily detected in these single crystal analyses. was probably unrealistic to assume that this mantling region grew instantaneously at the time of eruption. So I've turned that around and said, well, what could the growth rate of this mantling region be if we assume that we have a core of 105,000 years, we superimpose on that a mantle that grows over some period of time, what would the growth rate be? And it works out this is what the trend looks like depending on the length of that older core. So in other words, what's the volume of that older core? And those crystallization rates turn out to be sort of in the order of 10 to the minus 14 to the 10 to the minus 13 centimeters per second. And those are quite reasonable estimates for zircon growth based on some recent work that's been done to try to constrain those things. So we still have more work that we can do in terms of mass balancing things, but I wanted to really show you that we can reconcile these results to give us a tau of essentially 0 when we do a single crystal analysis, but again, recognizing there is some uncertainty there that may be on the order of a few thousand years. But sorry, that was my mistake. Let me see if I can get it back. Oops, down here. Yep. Okay. The tau that we get when we do our kind of averaging over a cross-section, and then this range of different taus that we got that were sequential as we went into the crystals. And again, I really want to emphasize, I really think these approaches are complementary, not contradictory. And what they're really telling us in this case, and I think there are further things that we can take out of this, is that based on the mass balance consideration, most of the crystal growth has occurred relatively recently, or relatively recent before the eruption. And that there are some relic old cores within the crystals that may have been either anticrys or just early evidence for the onset of this magma chamber. Thank you very much, and thank you for your patience.
And thank you, Mary, for your patience. That was an absolutely fascinating talk, and I have all kinds of questions for you later about that. We have one more speaker left. You brave enough, Carrie? She broke the speaker. Broke the projector. Okay, our next speaker is Carrie Cooper and Adam Kent, and the title of their talk is Constraints on Thermal History of Magmas from Combined U-Series Crystal Ages, Trace Element Diffusion, and Textural Information.
Okay, well, thank you. So what I'll be talking about today is really a synthesis of some work that Adam and I and our students have been working on in the last several years on Mount Hood, and so both at Oregon State and at UC Davis, and I'd like to thank NSF for funding for this. And the basic question that we're trying to address here is that by combining these different kinds of information, we feel like we can get some fundamentally different types of information out of the system than any of these things alone will produce. And the big picture question that we're working on here is really trying to get at this, which is a long-standing question, and we're not going to answer it completely, of course, but what fraction of time do these magma reservoirs spend in the mostly liquid regime versus the mostly solid regime? So, at relatively high temperature, it's going to be mostly liquid. It's going to behave rheologically like a liquid. At relatively low temperature, you're going to have a crystal mush, more or less, that is going to rheologically behave like a solid. And how much time does a magma reservoir spend in each of these sort of thermal regimes? And the approach then, as I mentioned, is that we're going to combine different types of crystal records. And collectively what we can do is constrain the total history for these crystals, the time that the crystals spent growing, and also something about the thermal conditions. And from that, we can get back and infer what's going on here. All right, so part of the motivation for this, and this is, of course, a very small figure summary slide, is by looking at different estimates of ages or timescale information, some from processes that are sort of, that again give you a duration rather than an absolute age, and some that give you an absolute age. And this compilation then shows uranium-thorium ages, radium-thorium ages in blue, and diffusion in the green bars, and crystal size distribution is the purple bars. And I should mention also that these uranium-thorium ages are only for major phases. They don't include the vast wealth of zircon data that are out there. Because we're focusing on the major phases because we have this other kind of information. And this kind of correlation has been noted, or this kind of observation has been made before, in that the U-series ages are consistently older than the CSD or the diffusion ages. And this has been noticed before and interpreted, broadly speaking, to reflect the fact that these different types of estimates of age capture different parts of the process. So our idea is then to take this and turn it on its head and use this in order to extract more information from the system by combining all of these different types of information together. And here's the data for Mount Hood, and here we have all of the different types of data, and we can actually combine these effectively to get some fundamentally new information. So conceptually what we're doing here is you can imagine some thermal history. The details of this aren't important, but let's just say that you have a magma reservoir which is cooling, crystallizing. You have occasional thermal pulses due to recharge or intrusion of subjacent magma or something like that, that then perturb this and then some cooling again. And we want to get some information about what's going on in this time window here and how do we constrain different parts of this history. So the first constraint that we have is the uranium series ages, and this gives us the total time that we have to work with. So this really provides the fundamental framework in which to interpret all of the other types of data. Then we can also add in something like the crystal sizes, so either crystal size distributions or simply the maximum crystal size itself, and get some information about the total duration of crystal growth. So what period of time did these crystals spend in this window between the solidus and the liquidus where they were actively growing? And finally, we can use the preservation of disequilibrium trace element concentrations and how that would have been modified by diffusion, give us a maximum amount of time that we could preserve these kind of disequilibrium concentrations. And then we can model that at different temperatures and constrain the amount of time that we spent above certain temperature windows, and thereby construct this more detailed and complicated history. And what's critically important here is that having this absolute time frame here, we can then put these in the context not just of a duration, but of a sort of percentage of the total time. Okay, so the case study, as I said, is Mount Hood. There's been a lot of work done previously in Mount Hood. The references got cut off here, but so Adam in 2010 published a paper in Nature Geoscience where he went through a lot of the evidence for magma mixing to produce andesites at Mount Hood. And what I'm showing here are just simply crystal size distributions of plagioclase for a number of Mount Hood lavas. And what you can see is that they have very consistent pattern where you have two crystal populations, what we're calling population 1 and population 2. And although this is a non-unique interpretation for crystal size distributions, we feel that we can uniquely say that these are two distinct populations, the larger one coming from a more silicic reservoir and the smaller population coming from a more mafic reservoir based on things like the trace element characteristics of these crystals. Now we also have then from Gary Epick's master's thesis published in 2012 earlier this year, we have information about the timescales of crystal growth from the uranium series crystal ages. For this population 2, for the rest of the talk I'll be talking just about the population 2, the silicic crystals, silicic-derived crystals. So radium ages are shown here in summary. For the plagioclase model radium age, for the two most recent eruptions, the eruption ages are shown here. And they agree within error of each other. The errors are relatively large due to uncertainties having to do with correcting for impurities in the mineral separates. But the uranium-thorium ages for the same mineral separates themselves are significantly older, an average of 145,000 years, although very large uncertainties on that due to limited spread in the uranium-thorium axis. But what we can say is that the minimum thorium age is about 17,000 years before present. So that's still significantly older than the maximum radium age that we get here. That provides us then our minimum total time frame for this crystal population. And then finally, we can use disequilibrium trace element concentrations. So this is just one example crystal out of many where the measured profiles, in this case of strontium, are very far away from calculated equilibrium profiles. And this limits the time that these crystals could have spent at high temperature. All right, so let's step through the different types of data and construct the picture here. Constraints on what I'm calling the total crystal lifetime are from the U-series ages. And in a little bit more detail, this combination of observations, so the uranium-thorium minimum age of 17,000 years, requires that some growth happened equal to or older than 17,000 years prior to the present, probably much older, could be consistent certainly with much older. In contrast, the radium ages, the radium model ages, require that there was some crystal growth less than 10,000 years before the present, or we wouldn't preserve the radium disequilibria that allows us to calculate these ages. So right away we can say that there was at least a two-stage crystallization history. So this is consistent broadly with a mix of, if we assume assume a simple two-stage history in that the most recent crystallization was at essentially just prior to eruption, then the minimum age of the old cores would be 21,000 years. The cores could be much older if the recent crystallization was also older. And you can have sort of additional crystallization episodes in there. We're working on some modeling to try to see what matches the combination of the apparent ages of uranium, thorium, and thorium, radium. In a general sense, if you have some sort of crystallization history here, we have a number of crystallization pulses. Each one of those will, if you calculate the apparent age at that particular time in the model age follows the apparent age follows the model time until you have an additional pulse of crystallization. Then the average age is decreased because you're mixing old and young crystals, but the averaging is different for thorium than for radium based on or due to the different timescales of decay for the different parent-daughter pairs. So we should be able to constrain something more about how these episodes are distributed in time, as well as how many of them there might be from a more detailed analysis here. But for now, what I want to focus on simply this observation. The minimum age for the cores is about 21,000 years. So we can also get then some constraints on the total growth duration, and one of the simplest ways to do that is simply to take the largest observed crystal size of about 3 millimeters and then assume some crystal growth rates. So these are typical plagioclase growth rates. And then calculate how long it would have taken to grow a crystal of that size. And so the growth durations that we get for, say, 10 to the minus 9 centimeters second would be on the order of a decade. For very slow plage growth rates of 10 to the minus 11, it's on the order of 1,000 years. But when you compare that to the total minimum crystal age of 21,000 years, we're still getting something that's a fraction of a percent up to only a few percent of the total time that these crystals existed, that they spent growing. We can also use the slope of the CSD to get another estimate of time scale of crystal growth. There are various ways that you can interpret this slope, but if you assume a steady state open system, you get a mean residence age from that slope, which corresponds in this case to up to about a century, so a little bit shorter. You can make the argument that this mean residence age may be actually more directly comparable to the average uranium series age. But in either case, the bottom line is that the growth durations that we're getting are a fraction of a percent up to maybe about 5% of the total crystal age. Now, of course, what we haven't accounted for here is the possibility that there was some dissolution of the crystals after they grew, so the total growth time could have been longer and you could have simply dissolved away part of that history. But we can actually put some limits on how much of that could have happened as well. So you can imagine a couple of scenarios in which dissolution might have been important. One of which would be if you have a magma reservoir which is sort of residing in the relatively high temperature interval, but still within the crystallization interval. Fluctuations within that could lead to a series of dissolution reprecipitation events. But we can use the diffusion and the preservation of these disequilibrium strontium profiles to put a maximum amount of time that these crystals could have spent in that sort of high temperature window. So if you calculate, for example, a residence temperature of 800 degrees, these are data for individual crystals, for individual profiles like this that Adam has modeled. And the estimated maximum residence age at 800 is on the order of decades to maybe centuries, which is still on the order of about 1% of the total crystal lifetime. So these kind of arguments, then, we can make. This limits how much time these crystals could have spent in this upper temperature range between the liquidus and solidus in this mostly liquid regime. And it also rules out continuous crystallization unless you're going to call upon growth rates that are incredibly slow and that it was spending its crystallization at the sort of near solidus conditions. All right, now another way you could envision that dissolution might be important is, let's say you had a largely low temperature history for wherever the region is that these crystals were being stored in. You could have brief excursions to high temperature, but because dissolution rates are on the order of about 100 times faster typically than crystallization rates, you could do a lot of damage in a short period of time in terms of these high temperature excursions. However, we can still place additional limits on that. We have a couple of different estimates for where the liquidus for this might be. One from melts. This is melts, not rhyolite melts, so for a rhyolitic liquid it's probably somewhat inaccurate. But we can also put a minimum liquidus temperature for this by looking at the maximum temperature from amphibole thermometry. Either way, if you're in this window of around 900 to 950 degrees Celsius, what this means is that you can only have them spend years to decades in that temperature window based on these data and still preserve the trace element profiles that we see. So the equivalent amount of growth then that would have been removed by years to decades of dissolution would have been 100 times more, so order of 100 to 1,000 years of crystallization could have been removed. If you add that to the total growth time, you're still talking about the order of 1% to 10% of the total crystal growth time or lifetime that the crystals spent growing. All right, so what are the implications of this kind of story for the magma reservoir at Mount Hood? Well, the fundamental conclusion is that the crystal spent the majority of the time at relatively low temperatures, and at those relatively low temperatures, the reservoir was probably on the order of 40% or more crystalline, in which case it was probably looking more like this and rheologically behaving more like a mush or a solid than as a liquid. And it's important to note that these crystals are present within the active part of the reservoir. These aren't just some sort of pod of magma that was intruded and then largely forgotten. These are crystals. The crystal size distributions are repeatable. The two most recent eruptions give us identical crystal populations, both in terms of the major and trace element composition and in terms of the crystal age. So it appears that this part of the reservoir is the part that is sampled over and over again as the silicic input for these Mount Hood magmas. And this also then implies that the system was relatively cold each time that it was reactivated. Now, you can look at and apply this approach to other volcanic systems. There are relatively few systems where we have enough different kinds of data to do this, but you could consider, for example, the Lesser Antilles or Mount St. Helens. To be a little bit careful here because these particular crystals for the CSTs and the diffusion may or may not be the exact populations that were dated by U-series, but based on just comparing the ages, what you can see is that there's a very similar pattern, so it suggests anyway at least a very similar pattern. Okay, so in conclusion, basically we can use the U-series ages to constrain a minimum total time, and again this could be much longer than this, but within that we can also say something about the total growth duration on the order of tens of years to maybe 1,000 years, even accounting for potential dissolution. That's still on the order of a fraction of a percent up to about 10% of the total time. And what this implies is that the region of crystal storage was very likely to be effectively solid for most of the history of these particular crystals. And then, of course, we're working on additional modeling to further constrain this at Mount Hood in particular, but this approach is really eminently applicable to other systems. And I think by looking at other systems and combining these kinds of data, we can get a fundamentally new take on what's happening in terms of these magma reservoirs. Thank you.
Any questions? The sessions, we can take them now. I can't see anything with the lights in my eyes. Maybe Carrie can. Any hands up? Oh, John.
Yeah. How do you get it so quickly from the liquidus down to the solidus? And then it must sit there for a very long time near the solidus and not crystallize.
Yeah, so the question was, how do you get it so quickly down from near liquidus temperatures to near solidus temperatures? And the short answer is that that's really sort of I guess a question that I would put on the modelers, for example, to understand that more. But the short answer, I think, is that the thermal histories that I showed were just examples. It doesn't necessarily have to get that far up close to the liquidus, but that still reinforces the conclusion that it's not spending very much of its history in that region in the upper end of the temperature window.
And as an advertisement, we're having another session on mushy zone magma systems. Thanks, John. On Wednesday and Thursday. So, yes, and we have a poster session tomorrow, right? Afternoon.